Okay, in this video I'm going to continue on with my tutorials bringing us from electromagnetism to optics. This is video number 20, or it's video number 1 in the Fresnel equation subsection. I'm going to discuss the reflection and transmission of light at normal incidence upon a surface. The previous videos to this which are relevant are numbers 19 and 18. In 19 I discussed the magnetic field boundary conditions, and number 18 I discussed the electric field boundary conditions. So we're now genuinely getting on to do a bit of optics, because what we're going to discuss, like I said, is the reflection and transmission, and that will give us things like the index of refraction, the incident amplitude and the excident amplitude, as well as the reflected amplitude. So the first thing we need to do is draw a diagram, and this diagram might actually become quite involved, so you'll have to bear with me. So first let's set up our coordinate system. But we're talking about 3 dimensions, so let's just, okay, so I'm sure you can understand what's going on here. As normal, I'm going to define Z as being this axis here, and the wave is going to propagate in the Z direction at the k hat unit vector direction. Alright, so I'm going to define the y-axis being down here, and the positive x-axis as being up this way. So notice, of course, this will be negative y, this will be negative x. Now you might say that's pretty obvious, but you'll see why I'm writing it down so explicitly in a moment, and this is negative z. Alright, so what we have is our electromagnetic field propagating in the direction as you look to the right. So the field looks something like this. And now let's say that the field, it could be plane waves, it could be anything you want, whatever way you want to think about it, okay? So here's our field propagating to the right, and has both an electric and magnetic component, which we will discuss in a moment. So let's think of the electric component first of all. So I'm going to say that I'm going to tell you that we know the electric field incident is polarized in the x-axis direction. So this is the incident electric field. And we know, of course, that it's going in the k-hat direction, so it's going this way. So it's moving with a certain speed. Now we all know at this stage that if something goes through, it changes medium, I suppose, then it changes speed. So I'm going to say that anywhere to the right of the origin is medium 1, and anywhere to the left of the origin is medium 2. So that means to the right of the origin we move with a speed of v2, and to the left of the origin we move with a speed of v1. Now, what else can we say about the magnetic field? Well, we know from previous videos that the magnetic field can be gotten as follows. It's the speed of c multiplied by the magnitude of the magnetic field is equal to the cross product of the propagation unit vector with the electric field. Now, in this case, the propagation unit vector is k hat. Notice, by the way, I have this particular k hat here and the k hat unit vector for the z direction. They are different. Okay, well, they are different in principle. It happens that they're both pointing in the same direction this time. So anyway, if we apply a right hand or left hand rule, whatever one you want, apply it according to this cross product. Apply it to the cross product, knowing that the electric field is polarized in the positive I direction, you'll find that the magnetic field comes out in the positive Y direction like this. So this is B incident, like that. Now we need to look at the transmitted wave. So I'm going to go for another color, let's say this purple. So once again it's moving to the right of the origin, so we have the speed of v2. Next, we need to look at the boundary conditions. Actually, we won't look at the boundary conditions yet. No, we'll keep the boundary conditions separate for the moment. So what we'll assume is this. We'll assume that the electric field doesn't change direction when it's transmitted. Let's just assume that for the moment. That means the electric field is still going to be polarized in the I hat unit vector direction. So this is the transmitted electric field here. It's going to be moving to the right, of course, once again, and the propagation unit vector is going to be here like this. Once again, applying our right-hand rule to this equation here, we'll find that the magnetic field doesn't change direction either. But what we do have is the amplitude at some stage will change. So this time it's the transmitted amplitude like this. And finally we need to discuss, let's go for blue, the reflected components. So we'll assume once again that the reflected components of the electric field do not change direction upon reflection. So here is the reflected electric field. That's the reflected electric field. But this time the wave is traveling to the negative z direction. And if we apply the right hand rule or left hand rule accordingly, we'll find that the magnetic field this time does switch sides, and the magnetic field is going in the negative y direction. So this is B reflected like that. And of course we have our boundary itself. Let's now actually sketch in the boundary, what's causing the reflection. Maybe it's a plane of glass, or pane of glass, excuse me. It could be here like this. And it's of course in the xy plane rather than, and has no component in the z dimension. So there's our interface there. So I've done that nice and slowly. Hopefully you'll be following me, because if you understand the diagram, you really do understand everything that's to follow. So now what we're going to do is look at the actual field. We're going to try and write the field. So let's look at the incident electric field. The incident electric field is a function of z and t. Okay, so I'll write it explicitly here, but not later on. So we have the initial amplitude, E0 incident, and then we have e to the I. Now the k value is going to change. Now why is the k value going to change? Well, we'll see this later on. You probably know the answer already. We know that the k value is 2 pi over lambda, and the wavelength is in actual fact a function of speed. So because the speed is going to change, the wavelength is going to change, and therefore the magnitude of the propagation vector is also going to change. So for that reason, what we really need to discuss is the fact that we have an initial propagation vector here, and we have a final propagation vector as well. Alright, so let's go ahead and just plug that in. So we get the initial propagation vector k1, it's moving in the z direction, and we need to have minus omega t and polarize it in the I hat unit vector direction. That's the incident electric field. What about the incident magnetic field? I'll just write it here, so it's B0 sub I. So it's e to the I k1 z minus omega t, and this time of course we know it's polarized in the j hat unit vector direction. So we now have our incident electric and magnetic fields. So let's do, I'll keep them black. So what about the reflected components? So this is the reflected electric field. So the amplitude is going to be different. Let's assume, because some of the field is after being transmitted, so some of the energy is after being lost. So we now have a reflected amplitude like this, and we've e to the I k1 z minus omega t. And this of course is in the I hat direction as well. So this is the reflected electric field. Notice of course that its polarization hasn't changed. It's still in the I hat direction like this. So nothing has changed. However, I need to put in, and I've left space for it, the fact that the k vector has changed direction. So the k vector is no longer going in the positive z, but rather is going in the negative z direction. I'm sure you can accept that. Now we're going to look at the reflected magnetic field, so B reflected. And it's similarly, we're going to get B0 sub r, and then we're going to get e to the I minus k1z minus omega t in the j hat direction. So it's e to the I minus k1z Now, we know, of course, that the speed of light multiplied by the magnetic field's magnitude is equal to the magnitude of the electric field. So we can actually get rid of B0 sub r in replacement, or in exchange for E0 sub r over the velocity. So it's going to be E0 sub r over V1. Now, the thing is though, because the direction has changed, we give it a negative sign here. Okay, because the direction has changed. Because if you look, the incident, let me just change my color. The incident magnetic field here was pointing in the positive y direction, but the excident magnetic field is pointing in the negative y direction. So we need to take this minus sign here in order to account for the fact that it's after inverting, it's after swapping phase by 180 or pi degrees, 180 degrees or pi radians. And now let's do the transmitted or excident wave. So the electric field transmitted is going to be E0 sub transmitted, E0 sub t, e to the I k2 sub z minus omega t in the I hat direction. E to the I and this is, of course, like I said, in the I hat direction. E to the I k2 sub z minus omega t in the j hat direction. Once again, we're going to remove B0 transmitted in favor of E0 transmitted, and we need to reduce its amplitude by a factor of V2 this time. So notice, of course, that we have to use V2 instead of V1 because we're after going into another medium and the speed is after changing and the wavelength is after changing as well, which cause our incident propagation vector to change to the excident propagation vector k2. Alright, so we're doing pretty well so far. Now I would suggest you just note down these equations if you like, because I'm actually going to write them out. Now the next thing we need to do is look at our boundary conditions. So I'll just write the boundary conditions which we saw in video number 19. The boundary conditions are as follows. So we have epsilon 1 E1 perpendicular is equal to epsilon 2 E2 perpendicular. So we find that it's discontinuous through the boundary. Next we have it's continuous parallel on the boundary, and the magnetic field then is continuous perpendicular through the boundary, but it's discontinuous parallel to the boundary. Like so. Now we need to apply these particular boundary conditions, and it's a pretty straightforward thing to do. So at z is equal to 0, so at the actual interface itself, the combined fields on the left and the right must join. So we'll say, let's look at the transmitted magnetic and electric fields. So in accordance with the boundary conditions, there are no components perpendicular to the surface. Now why are there no components perpendicular to the surface? Well, let's say the surface, like I said, is in the xy plane. There's the xy plane. We know that the wave is going in the z direction. That means the wave cannot exist in the z direction, but perpendicular to the surface is the z direction. There we've no perpendicular components. So immediately we can get rid of the perpendicular boundary conditions. So we need to apply this boundary condition here and this boundary condition here. So if we apply the first boundary condition, we find that the electric field should be continuous parallel to the boundary. Now this time the electric field is just going to be parallel. There is no perpendicular component, and as a result its magnitude, sorry, that's incorrect. There is no perpendicular component. So that means all of the transmitted amplitude is parallel. So I'll write the equation first, and then I suppose we can discuss it. So it's E incident, E0 incident plus E0 reflected is equal to E0 transmitted. That's what the boundary condition says. Okay, if we look at our equations. Now I might have had to I might have had to reduce E0 incident or E0 reflected if we also had a component parallel to the surface, but we don't in this case. And we'll see that when we talk later on about oblique incidence. And then if we look at boundary condition number 2, what we get is the following. We get 1 over mu1 E0I over V1 minus E0R over V1, and that's equal to 1 over mu2, which is the permeability of free space on the other side, and once again we get E0 transmitted divided by V2. And these are our boundary conditions as discussed in the previous video. Now let's just make a very quick substitution here. We know that the speed at which it's moving, so V2 is equal to n over V1. That's the definition of the index of refraction. So if we make a substitution whereby we allow beta to be equal to mu1 V1 over mu2 V2, we're able to incorporate the indices of refraction as mu1 N1, or excuse me, mu1 N2 over mu2 N1. Like so. And if we do that, we're able to recast the boundary condition as E0I minus E0R is equal to beta E0T. Provided we use that, we use this substitution here like this. So let's just write those boundary conditions one more time, have them together. So we have E0I plus E0R is equal to E0T, and E0I minus E0R is equal to beta E0T, like so. So these equations are easily solved for the outgoing amplitudes. So I'm just going to change my color, and let's go ahead and solve the outgoing amplitudes. So we find that E0I minus E0R is equal to beta outside of E0I plus E0R. And if you just rearrange that, what you'll find is that E0I is equal to 1 minus beta over 1 plus beta E0R. Alright, also we find that E0I minus E0R, so that's typo, E0I minus E0T plus E0I is equal to beta E0T. And this can be rearranged that E0T is equal to E0I outside of 2 over 1 plus beta. And these are our reflection coefficients. So we have these two. Now, just to, I suppose, can we play around with these? Is there any way we can rewrite these? So just bear with me for a moment. Once again, it might be worthwhile just noting these two equations on your own sheet of paper. But I'm just going to show you what happens if we just do a small bit of analysis here. So these results are very similar to those you would get if you looked at waves on a string. So let's say, for example, that the permittivities mu, the permittivities were close to that as they are in a vacuum. If we'll say the mu1 is approximately mu2 is approximately mu, what you would get then is that your coefficients become the following. E0r is equal to V2 minus V1 over V2 plus V1. And this is outside E0I. And you got E0 transmitted is equal to 2V2 over V2 plus V1. And this is all outside E0I. Now, why is this interesting? Well, first of all, if we see that the reflected wave is in phase, or it's the right side up, where V2 is greater than V1, or it's after going through a pi phase shift, it gets a pi phase shift where V1 is greater than V2, like that. Okay? And if you want to get the actual real amplitudes, then we take the absolute magnitude here like this. Alright? And finally, if we want to put this in terms of the indices of refraction, we can. It's not a big deal. So writing the indices of refraction, we get E0R is equal to N1 minus N2 over N1 plus N2 E0I, and we also get E0T is equal to twice N1 over N1 plus N2 E0I. So you can see here immediately we have our reflection coefficients already. So these would be normally known as our reflection coefficients, and this would be our transmission coefficient. Okay, so that was I suppose quite long, quite detailed, but hopefully that'll give you a good overview into reflection transmission at normal incidence. So thanks for watching. Please pass it on to your friends, subscribe to my channel, and you might also give me a comment on the comment box below.